Hello and welcome back to another episode of Mr. Walker's Chemistry. Today we're going to be continuing our unit on the periodic table. And we're going to be talking today about the periodic trends. That is, those trends that exist on the periodic table. In case you weren't aware, a trend is when something heads in a direction. For instance, we have things called fashion trends. Okay, in other words, Uggs were a fashion trend for a long time because the number of Uggs that people were wearing increased over time. Okay, that made it a trend. You can also have decreasing trends. Okay, and now we're into some new fashion trends. So the trend on Uggs is going out or something. All right. So the objectives for today, by the end of this video, you should be able to list the major periodic trends. You should be able to use those trends to make predictions, and you should be able to explain why those trends exist. So you're going to have to pull on your knowledge of atoms to know how this works. So the three big periodic trends, these are the three that we're going to cover. If you want to add them to your notes and leave some space so that you can, you're going to want to make some drawings, and you're going to want to be able to write in definitions. Okay, so the three trends are the atomic radius trend, the ionization energy trend, and the electronegativity trend. So you're going to need some definitions for these, and you're going to need to kind of draw an outline of a periodic table, and then some arrows to indicate what the trend is, so that you'll have that to study with. So atomic radius is, simply put, the distance from the nucleus to the outermost electron, to the valence electrons. Very simple. So how does this relate to the principal quantum number we learned about? Well, what do you think? Remember the outermost electron, the valence electrons. So principal quantum number is the amount of energy that an electron has, and the higher the energy, the further the electron is from the nucleus. Okay, so then if we relate principal quantum number back to the periodic table like we already learned about, we learned that the period number or row number is equivalent to the principal quantum number. So in that case, if the numbers increase as you go down, then the distance to the outermost electron should increase, so the atomic radius should increase. Think about it. Let it sink in. Rewind if you need to. Alright. The period number increases as you go down the periodic table. The period number is equivalent to the principal quantum number. The higher the principal quantum number, the further out an electron is, so the higher the atomic radius. It's all related, it's all connected. Alright, these things aren't just arbitrary. So in other words, if you're just that's the understanding of it. If you're more of a memorization type of person, just memorize that atomic radius increases down a group. Alright, and you decrease from moving left to right across a row. Well, okay, that one may not make so much sense. Your radius will decrease as you move from left to right. Well, let me explain that one. Let me see if I can draw a little picture here for you guys. Alright, so let's see. If I'm going to decrease the size of my atom as I go from left to right, well, let me do this. Let me go to the next slide. Alright, so here's your trend. Okay, atomic radius increases this way because you just have more shells. You have more orbitals. As you go this way, well, it decreases. Well, let's try and explain this. Alright, so what is increasing? Just inside of an atom, what increases as we go from left to right? Well, a few things. Okay, so let's say we're going from lithium to neon. This is number 3, this is number 10. So we're increasing the number of protons. Assuming that they're all neutral, we're also increasing the number of electrons. Well, if we're increasing the number of electrons, shouldn't they start to get further out? Yes and no. Okay. They don't really get further out, do they? Because you've got an s orbital here and a p orbital here, but they're still on energy level 2. They're still on principal quantum number 2, which really determines how far out they go. So no, they don't really get further out. But they do get pulled in more. If I've got more protons, then I create a stronger plus in the middle, a stronger positive pull in the middle of my atom. If I've got a stronger positive pull and my electrons are negative, it's more likely that I'll pull them in closer. All right. So let me say that again. All right. As you go from left to right, you increase protons. As you increase protons, you create a more positive pull on the electrons. So the electrons get pulled in closer, which results in this trend. Okay. So again, if you're a memorization person, going left to right, our radius gets smaller. All right. So next we'll move on to this, ionic size. Okay, this goes along with atomic radius, but now we're talking about the ionic size, which is the actual size of the atom. Okay, so most atoms do not exist as in the neutral state. Most exist as ions. And that's because they want to be, they want to have that full octet. They want to be happy. So they need to either get rid of or gain an electron to become happier. So the ionic size is based on the proton to electron ratio. In other words, if I have 2 protons and 1 electron, that would be a 2-to-1 ratio. So when atoms lose electrons, in other words, they become positive, they get smaller. And when they gain electrons, they get larger. Well, let's make sure that makes sense. Okay? If you are a proton and you're trying to hang on to 1 electron, it's pretty simple, right? You just grab it with both hands and you hang on to it with your life. It's not going to get away. Well, now all of a sudden, if I give you another electron to hang on to, you can only have 1 arm for each electron. So your bond, so to speak, your attraction to that electron is a little bit weaker. It's harder to hang on to 2 than it would be to 1. So as a result, those electrons get further away from you. They kind of pull you out a little bit more. So that makes your atom larger. Okay, here are some common ions and how their size would change. So here's lithium, the neutral one. Notice it has no charge. And then lithium ion with a positive charge. It gets a little bit smaller because now it's lost an electron. So those protons in there can hang on to these electrons a little bit stronger. The opposite happens when you become negative. Try and keep in mind that analogy that I just had. Remember, if you're just a proton, you've got 1 electron, you're hanging on to it, you can hang on to it with 2 hands. You can keep it in really close and tight to your chest. Well, all of a sudden now you've got 2 electrons to hang on to. That's 1 for each arm. They're pulling with the same strength, but you have half the strength now, so they're going to get out a little bit more. Okay, so just something about ionic sizes. This will probably show up on some exam that you take. All right, so ionization energy. Ionization energy, the definition is the energy required to remove an electron from an atom. So we've got that root word ion, and ionization, it's a process. So it's the process of taking a neutral atom and making it an ion. That's called ionization. And that requires energy. It takes energy to strip an electron away. Atoms don't usually want to lose electrons. And even if they do want to lose them, it still takes a little bit of energy. Not much, but a little bit, to pull that thing away from it. It's like, if you want to take a space shuttle and get it out of Earth's orbit, you have to put in energy. You have to give it a rocket boost to get it out there. All right. So this trend is kind of funky, but we'll look at it. Let's see if we can figure it out. But more about the definition, more ways to think about this. High ionization means that atoms hold their electrons very tightly. These are generally the noble gases. Atoms that are happy don't want to give up electrons, so they're going to hang on to them better. This trend is exactly the opposite of the atomic radius trend. So remember, the atomic radius trend increases down, decreases across. Well, this one's the exact opposite. It's going to decrease down and go across. And hopefully this makes sense to you, because if you're really, really, really big, I mean, you have lots of electrons out there. If you have hundreds of electrons floating around you, you're probably not going to notice when one goes missing. So yeah, it's going to be really easy to take one. But if you're hydrogen and you've only got one electron, it's really easy to keep an eye on that one electron, so you probably don't really want to lose it. So you're going to hang on to it more tightly. So here's a different way to look at trends. This is more of a graph type way instead of the chart that you saw before. Okay, so we've got atomic number across the bottom, so we're just going through the elements, and we've got ionization energy on the left as a measure of kilojoules, which is a measure of energy per mole. And we're going to learn a lot about the mole later. So if I have 1 mole of hydrogen, it will take approximately 1400 kilojoules of energy to remove the electron. For helium, it goes much higher, right? Because helium's happy. It's like, I don't really want to lose one at all, so I'm going to really hang on to these things. Now, those are your smallest atoms, hydrogen and helium, so they have the highest ionization energy. Whereas once we start getting bigger, if we look at just the noble gases, hydrogen, neon, argon, and krypton here, the ones that are highlighted, you start to see that even though they're still noble gases, it still gets easier to remove them because they're bigger. It's harder to hang on to those electrons. And for the others, it's generally increasing as you go across a row. So if we go from sodium to argon, we're going to increase ionization energy. So we're going, if you have your periodic table and you've got it sketched out, if you start at the top left, hydrogen, and you go across, you will increase ionization energy. So you can draw an arrow from left to right and write increasing ionization energy on it. And as you go down a group, so from hydrogen down to cesium, then it will decrease because they're getting bigger and harder to hang on to. And finally, our last trend, electronegativity. Electronegativity is defined as the ability to attract electrons in a chemical bond. When we start getting into chemical bonding, we'll talk more about electronegativity. But generally, those atoms that have higher electronegativity are trying to attract electrons. That's why it has the root word electron. Okay, and this is the same as our radius. Same as our ionization energy, rather. Okay, it increases across a period and decreases down a group. So if you memorize the trend for atomic radius and just remember that the other two are the opposite, you're set. Okay? I'm just giving you the reasons behind them in case you ever need to explain it. So electronegativity, here's the relative electronegativities. Please note that the noble gases are missing. Okay? So if we just start here at lithium, lithium has an electronegativity of 1. And if we go to fluorine, which is the highest, it has an electronegativity of 4.0. So fluorine really wants electrons. It's the hungriest atom in the world. It's really trying to become happy. It's got 7 valence electrons in its neutral state. It wants to have 1 more. Well, it's going to steal from anybody else to try and get it because it's the strongest. Okay, it's really hungry. So we'll notice down here that francium, cesium are the weakest. Okay, very large elements with 1 valence electron, so they're really wanting to get rid of that last one, and it's very easy for them to do so because they have low ionization energy. Okay, so the ionization energy of francium and cesium is very, very low, and it wants to get rid of one to be happy. So there you go. So fluorine and cesium would react very strongly and create a very big explosion when they do react. Okay, now you'll note the noble gases are missing. Think about why the noble gases might be missing. Okay, it's a critical thinking question. Put your knowledge of noble gases and electronegativity together. If you need a hint, how many valence electrons do noble gases have? And do they really want to gain or lose any? All right, think about that. So electronegativity, some questions about this. Based on the electronegativity, the En, okay, of an alkali metal and a halogen, which would gain and which would lose an electron. So if you need to, here's your chart. Okay, based on the alkali metals and the halogens, which would gain, which would lose. How would this affect their charge? So what type of ion would they become? How would this change the electron configuration? So you might have to draw out your electron configurations, the whole, 1s2, 2s2. If you need an orbital diagram, you can do that. That might help you. That's where you do the up and down arrows. And would this make an atom have a full valence shell or not? And this will go a lot more into bonding. So if you want to look up something, do sodium, do the Lewis dot structure for sodium, and do the Lewis dot structure for chlorine. What do you think is going to happen? Okay. Start being able to use your chemistry to predict. So go back, please review these trends, either memorize or understand, preferably that you understand them, and be sure to be able to draw them. If I were to give you a blank periodic table and say draw the trend, you should be able to do that. All right, so I hope that you learned something, and I'll see you next time.